Multimodal large language models, or MLLMs, often fail to see fine-grained details in images, even when they possess the latent capacity to do so. The main takeaway here is that we can unlock this hidden perceptual ability without any external labels or stronger models. This paper introduces CVPD, which stands for Contrastive Counterfactual Visual Process Distillation. CVPD is the first fully self-contained framework that allows an MLLM to discover its own visual blind spots and use them for dense, token-level self-improvement. By looking closer at what the model already knows but fails to use, we can dramatically improve its vision. Existing self-improvement methods for MLLMs suffer from a major limitation. They rely on coarse feedback or external tools. The main takeaway is that standard reinforcement learning only provides a single scalar reward for an entire response, which lacks detailed token-level guidance. On the other hand, traditional visual distillation requires privileged context, which has historically been constructed using external object detectors, segmentation models, or expensive APIs like GPT-4o. CVPD solves this by finding privileged visual context directly from the model's own internal behavior, bypassing the need for any external supervision. The core breakthrough of CVPD lies in how it defines and identifies a visual blind spot. The main takeaway is that a blind spot is an image region where zooming in sharpens the model's answer, while erasing it leaves the default full image response unchanged. This asymmetric behavior proves two things. First, the model has the capacity to understand the region when forced to look at it, and second, the model completely ignores this region under normal full image viewing. By identifying these regions, we find the exact areas where the model's default attention is weakest. To mathematically isolate these blind spots, CVPD uses a three-gate counterfactual criterion. The main takeaway is that this criterion filters out random noise and ensures we only train on highly informative regions. The first gate, latent capability divergence, ensures that cropping the region actually changes the model's prediction. The second gate, default perceptual invariance, ensures that blurring the region does not alter the full image prediction, confirming the model was ignoring it. The third gate, epistemic sharpening, ensures that the crop reduces the entropy of the prediction, meaning the model becomes more confident and decisive. Once a blind spot is discovered, CVPD uses it to perform contrastive self-distillation. The main takeaway is that the model learns from two opposing internal teachers at the same time. The crop-conditioned view acts as a positive teacher, pulling the student model towards sharper, localized perception. Meanwhile, the ghost-conditioned view, where the region is blurred, acts as a negative teacher, pushing the student away from its default inattentive behavior. A reference policy anchor is also used to ensure the model does not lose its general language and multimodal capabilities during training. The effectiveness of the three-gate curation is clearly visible when analyzing candidate image regions. The main takeaway is that random, uncurated regions merely perturb the model, whereas curated blind spots provide highly separated and clean training signals. Without curation, random crops and blurs cause similar levels of divergence and actually increase prediction entropy. Once the counterfactual criterion is applied, ghost side noise is suppressed by 24 times, and the entropy change flips from negative to positive, proving that the selected crops make the model significantly more decisive. CVPD was evaluated across 12 visual perception and reasoning benchmarks, showing outstanding results. The main takeaway is that CVPD consistently outperforms all self-evolving baselines without a single performance regression. On Qwen-VL 8b Instruct, CVPD achieved massive gains on tasks requiring precise localized attention, including a 3.6-point increase on OCR bench and over 3 points on MM* fine-grained perception and logical reasoning. Crucially, these targeted perception gains did not come at the expense of broader multimodal capabilities, which were maintained or improved. While CVPD represents a massive step forward, there are still limitations to address in future work. The main takeaway is that our current region proposal methods and data yield can be optimized further. Currently, CVPD relies on simple grid partitions and self-grounding boxes, which might miss highly irregular or non-rectangular blind spots. Additionally, the strict three-gate criterion has a yield rate of about 17%, meaning many images are discarded. Future work will focus on more flexible region proposals and improving the data efficiency of the discovery phase. In conclusion, CVPD proves that MLLMs already encode far more visual information than they typically show. The main takeaway is that we do not always need larger datasets or stronger teacher models to improve vision. We simply need to teach models how to look at what they already know. By turning internal blind spots into dense contrastive supervision, CVPD opens up a highly promising, fully self-contained pathway for the next generation of self-improving multimodal models.